Okay, now that we've looked at the first derivative test for max and min, let's go ahead and look at some applications here. So first one here, we have a profit in thousands of dollars from the sale of X units of a certain prescription drug is given by a certain function that happens to be a natural log function, natural log of negative x cubed plus 3x squared plus 72x plus 1. And we're also told that x is in 0 to 10, so thousands of dollars here. So we have some limitations on our function here. We want to find the number of units that should be sold in order to maximize the total profit. All right, so the first thing we want to do here is we want to go ahead and take the derivative of this. Okay, so this is a chain rule type of problem where we have the natural log of this whole value here, which is 1 over that entire value. And we're going to go ahead and multiply by the derivative of this polynomial function that's in parentheses. And we're going to go ahead and just write it as one rational expression here. Okay, so remember that the chain rule will sneak in on you in various things. Please don't ever forget about it. And so here we're going to go ahead. We're not going to worry about where it is not defined, seeing as the whole function won't be defined at the points because ln of 0 is not defined, and we're not going to worry about that part of it. And we're also limited between 0 and 10. Okay, so anything that was negative, it wouldn't be in our domain that we're looking for. Okay, so we want to go ahead and solve for the derivative equal to 0. What's going to happen is when our derivative is set equal to 0, the denominator piece, of course, is going to get multiplied by 0 and go away. So we're dealing just with the numerator here. So we have the numerator, negative 3x squared plus 6x plus 72. We're going to set that equal to 0. We can go ahead and factor out a negative 3. And when we factor out a negative 3, it gives us a nice little quadratic that we can go ahead and factor. Again, you can go ahead and use the quadratic formula. You will end up with the same values. And we end up with x minus 6 times x plus 4. We're going to set each of those pieces equal to 0. We either end up with x is equal to 6 or x is equal to negative 4. Now, negative 4 is outside of our domain from 0 to 10, so we're only going to go ahead and test the value 6, okay? And when we're talking number of units, obviously we don't manufacture negative number of units, so just in a common sense type of thing, even if you didn't have this restriction, we wouldn't want to go ahead and use the negative 4 value. So if we're going to go ahead and just test 6, we're going to test the numbers to the left and to the right, so 5 and 7 are great numbers to test. And what we find out is at 5, when we plug in 5 into our derivative, we end up with a positive value. When we go ahead and plug in 7, we get a negative value. And remember, this makes it a maximum because we have a positive slope to the left, a negative slope to the right. So this is a maximum point. Okay, so x equals 6 is a maximum point. So if we want to know the maximum profit, we're going to take that 6. We're going to go ahead and plug it into the original function. And we end up with 5.784. Remember that our units were in thousands of dollars. All right. So you could go ahead and just write the monetary amount of in thousands. Okay, because if you multiply this by 1,000, it moves the decimal over to the right 3 places, and we end up with $5,784. So be really careful. Don't truncate because you may need these numbers to actually give the exact answer on this. Right? Let's go ahead and look at one more. So here we have a cost function for a product given by this lovely cost function here. It's a cubic. All right, we have x cubed, an x, and just a number. And we want to find the production level And here they tell us that's going to be the value of x that will produce the minimum average cost. So here we're looking for the exact opposite we were before. We're looking for a minimum. So first of all, remember they're talking minimum average cost. And you did this in your discussion before. And what we're going to go ahead and do is we're going to go ahead and get our average cost. Remember, we have to take our cost function divided by x first. So when we go ahead and do that, we end up now with a quadratic, all right, and a fraction at the end. And this is totally okay. You can write it either as a fraction or with the -1 exponent. Either way is perfectly okay, right? And then what we want to go do now is take the derivative of this average cost function and set it equal to 0, all right? So we go ahead, take the derivative. I'm going to go ahead and you could leave the exponent the same as it is, or you could put it in the denominator, whatever is best for you. All right. But here they have it both ways. They have it here as a negative exponent, and we also have it here in the denominator. I kind of like the idea of a fraction because when I go ahead and move stuff around, I go ahead and add this to the other side, and that allows me to see that denominator. I can go ahead and multiply both sides by x squared, which gives me this cubic on this side is equal to just a number. And then I have to go ahead and divide by the 4,000th, and then go ahead and cube it. Okay, and when I go ahead and put this in my calculator, I end up with the number of 120. Okay, so if you want to go ahead and locate the cube root, if you use the math key on your TI-83 or 84, it'll be option 4. All right, and then you can just go ahead and type your cubic root in here, and we end up with 120. Right. Go ahead and test 120 on the number line. I'm going to test 100 and 150. You could go closer to that if you would like. It really doesn't matter. Going by 10s or 20 is okay. You're just trying to find nice numbers to the left and to the right, whatever's easier for you to work with. When I go ahead and plug 100 into the derivative, I get a negative value. When I plug 150 in, I get a positive value. And this lets me know that my slope to the left of this number is negative. My slope to the right of this number is positive. Therefore, I have a minimum at x is equal to 120. All right. And all we needed was the x value because they asked us for the value of x that will produce the minimum average cost. They did not ask us what the minimum average cost was. If they had, then we would go ahead and take our 120, plug it into our original average cost function, and we could go ahead and find that value.